Here we have calculus problem on infinite series. Okay, let's go with the question. Use a sequence of partial sums to determine whether the series converges or diverges. Here we have an infinite series and we have to check whether this series converges or diverges using the sequence of partial sums. For that, first we have to write the nth term of the given series, that is 1 over n times n positive 1. So the stuff we have over here represents the nth term of the given infinite series. Okay, now let's find some partial sums of the given series. That is, let me find the first partial sum. First partial sum is nothing but the sum of first one term of the series. Sum of first one term is nothing but the first term of the series. So to get the first term, what I have to do is I just have to plug in n equals to 1 into the nth term of the series. When I plug in n equals to 1, I'm getting 1 over here. 1 positive 1 will be 2. 1 times 2 is 2. So that is, I'm getting 1 over 2. Okay, now let me get the second partial sum, that is S2. Second partial sum means that is the sum of first two terms. Already we know the first term it's 1 off, and to get the second term, what I have to do is I have to plug in n equals to 2 into the nth term of this series. So when I do so, I'm getting 2 over here. 2 positive 1 will be 3. 2 times 3 is 6. So the second term of the series is 1 over 6. So to get the second partial sum, I have to add the first term and second term. Okay, now let's get the third partial sum. Third partial sum means we have to add the first three terms of the series. Already we know the first term and second term of the series. So let me write them 1 over 2 positive 1 over 6. Now we have to add the third term. For that we have to plug in n equals to 3 over here. So when you do so, 3 times 4, that is I'm getting 1 over 12. Let me get the fourth partial sum. So that is equal to, already we know the first three terms, 1 over 2, positive 1 over 6, positive 1 over 12. So fourth partial sum, S4 means like we have to add the first four terms of the given infinite series. So I have added the first three terms. I need the fourth term. So for that I have to plug in n equals to 4 into the nth term of the series. Then I'm getting 4 times 4 positive 1 is 5. That is I'm getting 1 over 20. Okay, now I got the first partial sum, the second partial sum, third partial sum, fourth partial sum. Okay, now what I'm going to do is I'm going to form a sequence with the partial sums of what I've got over here. So that is S1, comma S2, comma S3, comma S4, and it keeps going. Okay, so now how do you have to decide so whether the given infinite series converges or diverges with the sequence of partial sums? Okay, so if the sequence of the partial sums converges to a finite value, then the given infinite series also will converge. In case the sequence with the partial sums diverges, then the given infinite series will diverge. So now we have to find whether the sequence with the partial sums converges or diverges. That's what we have to find. So how do you have to decide so whether the sequence converges or diverges? For that, we have to look at the patterns of what we got for the first partial sum, second, third, and fourth. Okay, particularly I notice the pattern in the fourth partial sum, because in the fourth partial sum I have some more number of terms compared to the third partial sum, second partial sum. Okay, when I consider the first term of the fourth partial sum, that is S4, is just 1 off, which is less than 1, 0.5. Its value is, let me write over here. Okay, let me write it. And when I consider the second term over here, 1, 6, this is less than the previous term, 1 off. So, and its approximate value is 0.16. And also when I consider the third term, it's less than the previous term, 1/6, and its approximate value is 0.08. And when I consider the fourth term over here, 1 over 20, its value is 0.05. Okay, now look at the pattern over here. So when I consider the fourth position, the value of the first one is 0.5, the second one is 0.16. So it's decreasing. So again, from 0.16 to 0.08, again it's decreasing 0.05. So when I consider the last term over here, its value is 0.05, and it's too small and it's close to 0. So what if I find the fifth partial sum, and what will be the value of the fifth term in the fifth partial sum? Definitely it will be less than this 0.05. That is, it will be too small and close to 0. So in this way, when I find partial sum like a 10th partial sum, 11th, 20th, 100th partial sum, so like the value of the last term will be too small and it will be very close to 0. Okay, so for example, if I add all the terms over here in this infinite series, then I'll be getting 1 over 2, 1 over 6, 1 over 12, 1 over 20. So in this way it will keep going. So that is, I am adding infinite number of terms in the given series. So when I add the infinite number of terms in the given series, so definitely the last term will be 0. So even for the fourth partial sum, the last term is 0.05, it's very close to 0. So when I add infinite number of terms in the given series, because the question clearly says that we have to take n is equal to 1 to infinity. So I consider infinite number of terms in the given series. When I do so, so the value of the last term will be 0. So what does this pattern indicate? So this pattern indicates that there is a chance for the given series to converge. Okay, so now we get some idea that the given series may converge. So how do we have to decide, and to what value it converges? So whenever a series converges, then it has to converge to a finite value. So how do we have to decide that? So for that, what we have to do is we have to write, we should try to write explicit formula for the sequence with the partial sums we have over here. So how do we have to write the explicit formula? So for that, we have to write the value of the first term S1. It's 1/2. We know that here. And to get the value of S2, we have to simplify the addition of two fractions over here. So to add the two fractions over here, we need the same denominator for both the fractions. So for the two denominators 2 and 6, the least common multiple is 6. So we have to get, instead of 2, so we must need 6 over here. For that, I have to multiply both numerator and denominator of this fraction by 3. So when I do so, I'm getting 3 over 6 positive 1 over 6. And so here we have the same denominator, so we can take the denominator in common. And when I add the numerators, I'm getting 4. 4 over 6 can be simplified to 2 over 3. Okay, now let's do the same thing. Okay, now I got the value of S2, which is 2 over 3. Okay, now let's get the value of S3. For that, we have to add these three fractions. Okay, let's consider the new denominators 2, 6, 12. So what's the least common multiple for 2, 6, and 12? So it's the least common multiple is 12. So we have to make each denominator as 12. So to make this denominator as 12, I have to multiply this fraction by 6. When I do so, I'm getting 6 over 12. And I have to multiply this fraction by 2, then I'm getting 2 over 12. And I can keep this one as is because already we got 12 in denominator, 1 over 12. So now we can take the common denominator 12. When we add them, so 6 plus 2 is 8, 8 plus 1 is 9. 9 over 12, it gives me 3/4. Okay, now let's, 3/4 is the value of S3, that is a third partial sum. Okay, now let's find the value of S4, that's a fourth partial sum. So when I consider the denominators 2, 6, 12, 20, so the least common multiple is 60. So we have to make each denominator as 60. So to make this, the denominator here as 60, so I have to multiply both numerator and denominator by 30. Then I'm getting 30 over 60 positive. So here I have to multiply by 10. Then I'm getting 10 over 60. So here I have to multiply by 5. Then I'm getting 5 over 60. And here I have to multiply by 3. I'm getting 3 over 60. So now we have a common denominator 60. And when I add the numerators 30 plus 10, 40, 45, I'm getting 48 when I add the numerators. And so both 48 and this 60 have the greatest common divisor 12. So when I divide 48 by 12, I'm getting 4. When I divide 60 by 12, I'm getting 5. So the value of S4 is 4/5. Okay, now I got the values of the terms in this sequence S1, S2, S3, S4. Okay, now let's try to get a explicit formula for this sequence over here. So when I look at the first term over here, the denominator 2 is exactly 1 greater than the numerator 1. So let's see, we have the same pattern in the second term as well. Yes, the same pattern we have in the second term as well, because the denominator 3 is exactly 1 greater than the numerator 2, and we have the same thing in the third pattern. So the denominator 4 is exactly 1 greater than the numerator 3, and this 5 is exactly 1 greater than the numerator 4. So we can write the explicit formula with the kth partial sum, that is Sk. Okay, so if I assume k as the numerator, then the denominator has to be k plus 1, because according to the pattern we have over here, the denominator has to be 1 greater than the numerator. So if the numerator is k, the denominator has to be k positive 1. Okay, now to check whether the sequence formed with the partial sums converges. So what I have to do is I have to take infinite limit for k on both sides of this explicit formula. Okay, let me do it. So before that, I'll erase the stuff so that I'll find space to work on it. Okay, now in this explicit formula, I'm going to take the limit, infinite limit on both sides for k. That is limit k approaches infinity. Sk equals to limit k approaches infinity, k over k positive 1. Okay, limit k approaches infinity. Okay, here we have nothing more to do with the numerator. We just have k numerator. Okay, in denominator, what we have to do is like we have to look at the degree of k. So because k approaches infinity, so when I look at the degree means the largest exponent of k. So there is only one term k with the exponent 1. So the largest exponent of k in denominator is 1. So we have to factor k with the largest exponent, that is k. So when I factor k out, what do I get inside the parenthesis over here? To know the stuff inside the parenthesis over here, after k is factored out, I have to divide each term of this expression by the one I factor out. So when I divide this k by this k over k will just become 1. When I divide the second term 1 by this k, I'm getting 1 over k. So this k will cancel out. I'm getting a limit k tends to infinity 1 over 1 positive 1 over k. Okay, now we can plug in this limit for k over here. Then I'm getting, let me do it over here. So 1 over 1 positive 1 over infinity. Then I'm getting 1 over 1 positive. So whenever I divide a finite value, that means non-zero number, by infinity, always it will result 0. That is the value of 1 over infinity is 0. So we get 1 over 1 positive 0 is just 1. So still it is equal to 1. Okay, so when I evaluate the limit k approaches infinity as k, I am getting a finite value 1. So clearly this sequence, the sequence formed with the partial sums converges to a finite value 1. Since the sequence with the partial sum converges to 1, so the given infinite series also will converge, and it will converge to the same value to which the sequence of the partial sums converge. So therefore, the value of the given infinite series equals to 1.